So we already talked about all of these up to this point. In the last video we stopped here, I discussed this. So if you set the first item, which is at index 0 to 3.99, when a array is actually an integer, what do you think is going to happen? Is 3.99 an integer? No, 3.99 is a floating point. So what it's going to do is to keep the whole number part and disregard the 0.99, the decimal fraction. So it's going to replace the first item in the array by 3. First item was 1, right? And so it's going to become 323. The data type of the array will not change because you're trying to put in a number that is of the wrong data type. You can try to fill up the entire array with minus 3.7, and again the data type remains integer, and then it disregards whatever you have in a decimal place and keeps only the whole number part, and it becomes minus 333. So when you run it, that's exactly what you get. Why is this off? Because I'd run it before. So if you want to get the exact result, you'll have to rerun this first, and now it's 123, and then you can run this and it's going to become 323, and so on. In the cell below, I show 3 ways to create floating point arrays. So we can actually control the data type of the array when we create it. First approach, which we already talked about, is to have at least one of the items in floating points, and then it's going to automatically create a floating point array of 11.0, 12.0, and 13.0. Good programming practice, just set the data type for each of them explicitly, right? Second approach, provide a second argument to the numpy's array function. So numpy.array, provide the list and then provide a second argument, and you always separate the arguments by commas. So d type, which stands for data type, equals float. Then it knows even though these numbers look like integers, it will create floating point precision numbers and store them into your A array. And the last approach is using the .asType function, which works on arrays in NumPy. So you create the array. Right now, if you stop the array will be what data type? Integer. Then you do a .asType, and then you can specify whatever data type you want. And in this case, we want floating point precision numbers. And so these 3 will give exactly the same results. This approach is very robust because even multiple lines after you have already created the data type, you can change the data type of the array by using this function on the array. So you already created a array, say as an integer, if we did this, and then you can come down here and do .asType on that array, which is currently an integer, and then it will, actually here we're converting it to integer, so that presupposes this is floating point. We could have done this and then change this to float, right? Like so. And then the entire array becomes a floating point. It was an array, it was an integer array at this level. Or you can do this. It's not responding. Control Z, Control Z. You can do this. You create a floating point precision array, and then you convert it to integer array. So the asType is very flexible. You can use it to switch data types around even after they've been created. And when you run these, you obtain these results. 3 different ways to get the same result, which is an array of double point precision numbers. And then you can use the asType int to convert the array to integer. There is also another way to create arrays. Instead of using the numpy.array, you can also use numpy.arange, and that works just like a range. Extremely important. Students make this mistake a lot. They try to use range to create arrays of vectors. No, range gives you a different result. To get a range that is an array, you use a range, right? Array range. Very important to realize that this is what you'll be using a lot in those exponential decline models and so on. We'll look at it in practice here. First off, the range function, which we've talked about before, which will be what I've selected so far, it will start from 0 and stop at 5, right? Because it doesn't get to 6. That will give you a range data type. Well, if you want an array, you will use numpy.arange, which stands for array range. So the range function, again, comes from standard Python, but the arange function comes from numpy. So you will have to import numpy to be able to use the arange function. But you don't need to import numpy to use range. Again, they're very different. If you want an array that goes from 0 to 100 or from 100 to 200, what you need is numpy's arange. If you want an array that you can do calculations on, but if you just want an iterator, something to use in loops and so on, then range from the standard Python will do. So 0 is the start, 6 is the stop, this is the stride, and you can always change that as needed. So one use case, the tvec, which you had worked on in lab 2. Here we can create it using numpy.arange. So it will start from 0, stop at 14. So you have time, which could be in days, months, years. Go from, let's assume it's years, you're going from year 0 to year 14, right? And then you want to find the corresponding flow rate for those 14 years at once, right? We want the calculations to be done at once. And that's what we refer to as vectorization in programming languages like Python or MATLAB. So this is just one equation, but because this data type is a vector, so the entire equation will be applied to the entire vector, and what you will get here will be a vector, not a single number. So you will have all of the 14 rates corresponding to all of the 14 times. So that's very important. So this is similar to what you did before. Initial flow rate, initial decline rate in percent per year. And then we use the we use the numpy's arange, which stands for array range. You can think of it in that form. And that will give you an array that goes from 0 to 14. And then you will use that array in this function. Very important too. Students make the mistake of trying to use the math.exponential, which you used in lab 2. The one you used in lab 2 applies to primitive data types, single values, right? If you want to use an exponential function that will apply to an entire array, an entire vector, or an entire matrix, what you want is numpy's exponential function. And same deal with all the other functions in numpy. They will apply to an entire vector or matrix, but that is not the case with the standard functions in Python or even in the math package. So the math package will give you an error if you try to do math.exponential and then you are providing a vector. So important to use numpy in that case. That will save you a lot of headache in the labs. And of course, this is a constant value. And this is also a constant value. So this will be a vector or a single number. it will be a vector because tvec is a vector. And then you can print it, you will get the 14 numbers, right? You can print A, which is the array we just used here for illustration purpose. So this is not relevant to the calculation, right? Because you don't see A in any of the calculations. Good, so you see an array A is just 0, 1, 2, 3, 4, 5. It stops at 5, it doesn't get to 6, because that's how Python works. That's the A printed at the very end. Then we calculated Q, and it's a vector of 14 numbers, and you already know these numbers should decrease. So whenever you calculate decline models, right, you predict production with decline models in your labs, in your quiz, in your finals, always check that it declines, right? Because production declines through time. The energy of the reservoir decreases, and then, like you saw previously, I'll also show you some plots shortly. Check that your results decline. So if it isn't declining, then you know you have done something wrong. You can get the shape of an array using the shape function. That's straightforward enough, right? A.shape for an array A. And that tells you 6 comma, meaning there are 6 items. And then the comma is not multi-dimensional. So np.shape of A, these are 2 alternative ways of getting the same result. You can either call the shape function directly on the numpy array, or you can do numpy.shape function and then provide the numpy array as an argument to the function. You can print the size, and that will tell you the number of elements in the A array, which is 6 in this case. You can print the number of dimensions. That's what ndim is. These are functions defined in NumPy to work on NumPy arrays. And the number of dimension is 1, right? This is a row vector, so the number of dimensions is 1. If it's, you'll later see examples that are multi-dimensional, like 2 by 2, 3 by 2. These are 2-dimensional matrices. Then the ndim will show 2 in those cases. You can have 3 dimensions or even more. There's also another way to create floating point arrays using arange, which is to list out the... No, that's not what's going on here.